Section 7.5, the center of mass. So the center of mass is a point that represents the average location for the total mass of a system. This is also known in many cases as the balance point of an object. So with my ruler, for instance, right? The quick way within a long object like this to find the center of mass is actually just support it with two fingers and then move those fingers closer and closer together. And where they meet is the center of mass of the object. And it's right in the middle for this ruler because the ruler is a uniform distribution of mass. So this is saying that we have equal mass on this side versus equal mass on the other side. And this can be really useful because if we know that that is the center of mass point, and that's going to be a point where it's balanced, it doesn't tip one way or the other. It can also be really good for spinning things around, right? It's able to rotate about the center of mass, which is something we'll be looking at a bit more in the rotation section. Center of mass is also something that comes up with various weapons, like this Saxon knife or sword is a common place where you care about the balance point of the sword. Right, so you care about where there's equal weight on one side versus the other. And depending on the style of sword fighting, right, you might want that balance point to be closer to the handle or further up. So this looks like it's closer to the handle than the very geometric center, but it's not all the way at the handle's hilt, right? So that can give you some sense of the center of mass. Now, how do we calculate that? Well, if you wanted to calculate for an extended object like this, you would need to do an integral. You need to use calculus to sum up all of the mass over here, the less mass over here, but there is still mass over there, right? And trying to account for all of those different things. We're going to start with a simpler imagination, which is that if we just have two masses, such as if I strapped on two giant masses to my ruler here, where would the center of mass be depending on where those masses were located? Well, that's what's depicted here, that we have mass 1, it's at some distance, like from the end of the ruler. Say I put one of the masses at 2 inches. And then mass 2, I can put it some other distance from the end of the ruler. Maybe I put it at 12 inches. Where's the center of mass of those two masses? Well, it's going to be somewhere in between 2 and 12, but it's going to depend on how massive each of those objects is. Right? So that's the way we can calculate it, is we can multiply the mass times the distance it is, and it's sort of a weighted average, where we're averaging out those two distances, x1 and x2, but we're weighting it by how much mass each of them contributes and dividing by the total mass here. And this will tell us the new balance point with those added weights. Okay, with those added weights, the new balance point has shifted. It's closer to M2. I'm guessing mass 2 is bigger in this case. So maybe my balance point ends up somewhere over here instead of in the center. This is all hypothetical since I haven't strapped on a bunch of masses to my ruler, but hopefully it gives you some sense of how you could do the calculation. So this is a very handy way to calculate the center of mass in a single dimension, which we often will do with long objects like the one shown. Now, how does this relate to everything else we've been learning about this chapter? It's always a good question to ask. So what we're going to consider is, what if each of those masses is actually moving a small amount, some delta x? Well, mass 1 is moving some delta x1 instead of position 1, mass 2 is some delta x2. If we fill those in, if we divide both sides by delta t, now we have delta x over delta t, a change in position over a change in time. That sounds like our velocity. And notice on the top here, when we write it in terms of velocity, we have mass times velocity of 1 plus mass times velocity of 2. What quantity is mass times velocity? Why, that's just our momentum, the total momentum of the system. of mass 1 and mass 2. What does this mean? Well, in an isolated system, so again, assuming that you've already determined it's an isolated system, the total linear momentum does not change. Therefore, the velocity of the center of mass also does not change. So in my equation for the speed of the center of mass, that point that's the effective center of even two objects that are not connected, there's a center of mass of these two objects. If these two objects are moving in an isolated system, their center of mass is going to be constant throughout. Let's look at this with some previous examples. So we could go back to the two-dimension collision of, say, pool balls, right? The center of mass is at a point between them. It's closer to the blue ball because the blue ball is more massive than the red one. But they're all moving and it has some velocity. The collision happens, the center of mass keeps moving in the same direction. It is unchanged by the collision. Meanwhile, ball 1 and 2 have totally changed direction. They've changed their amount of speed too, while the center of mass velocity remains constant. Whoa. We could even go to the ice skater example, right? The ice skater example, beforehand, the center of mass velocity was 0 because the initial momentum of the system was 0. They're just standing there. They're doing a nice job standing there, but they aren't going anywhere. What about after? Center of mass velocity after, we could calculate the total momentum after, right? The mass of the man times the man's velocity plus the mass of the woman times the woman's velocity divided by the total mass. And we get something that's nearly 0, 0.02 meters per second. That's tiny. At that point, it could possibly just be due to sig figs and the other velocities, right? That's essentially 0. So the center of mass velocity, even when they go from not moving to suddenly shooting off, their center of mass is still right in the middle, right where they were before. So this is another illustration of the conservation of linear momentum, which is the big idea of this entire chapter. I hope you've seen some different examples now of how you can apply the conservation of linear momentum and how it can make solving problems much easier overall. And that wraps up Chapter 7, taking a look at impulse and momentum.